So our next talk is, I was really interested when I saw this a talk submitted. It's an interesting usage of Accumulo, so I'm glad it was submitted. Dr. Rod Moten from ProArc is going to be talking to you guys about this. Thanks.
Good afternoon, everyone. I hope you enjoyed your lunch. I was tempted to start doing a dance move to keep it interesting, but that might make you throw up your lunch, so I'm not going to do that. So my name is Rod Moten. I'm from a small company in Baltimore called ProArc. We're a startup. There's only 6 of us. We hired a 6th person last month. And we do work for primarily Department of Defense and advising them on enterprise architecture, and we also help them with project management. So what I'm going to talk to you about is related to a problem that one of my customers had, and that there's a need to pass messages between consumers and producers. And you have to ensure that the consumers can only access information that they are allowed to have a privilege to. So we thought about using Accumulo because Accumulo has the cell level protection, and I'll talk to you more about exactly what we did. So first, let me just go over what I'm calling confidentiality protection. So there's actually 2 definitions of this, and I'm taking different definitions. One is ensuring that you can protect the identity of people who submit data. This is not that definition. This is just ensuring that confidential information is only accessible by folks who have the correct privilege to see that. So a good example, and I'm sure many of you related to this since I think majority of people here are working in the government space, is ensuring that people with secret clearances can only read secret documents. Now, usually the way you implement or apply confidentiality protection is you may have some artifact, a document, it could be video, and you're going to tag it with some attributes that represent a confidentiality level. And usually what you do is you tag portions of an artifact. So like you'll tag the individual paragraphs, you can tag frames on the video, and the entire artifact will get the confidentiality level of the highest part. So an example of this is shown here where you may have some document and the different paragraphs get marked with different levels. So you have public at the lowest level, then confidential, then trade secret. And this is completely made up, this example. But anyway, you mark the individual paragraphs, and then you mark the entire document at the highest level, which would be, in this case, trade secret. And one benefit of doing this is that you can take that single document, and if you want to make it available to people at a lower level, you can just easily strip out things that made it the higher level. So what if you need to do that for data streams? So obviously it's easy for a single document, but what if you have data streams? So like, for example, you have streaming video. Well, what you could do is you can begin to mark each frame or a collection of frames. And by frame, I don't mean just like a video frame, but any fixed size amount of data that you're transporting. And if you do that, then you can assign consumers of those frames different access levels, and they should only be able to read what they have access to. Now, the thing about doing this, having confidentiality protection on data streams is you can't allow the consumers and producers to directly connect. So you can't have a producer that has some IP address, and the consumer can read directly from that producer's IP address. You're going to need some broker in the middle. That's to guarantee that the consumer isn't connecting at the wrong access level. So one way you can think of doing this is using a traditional queuing system like QPid or RabbitMQ, you know, pick your poison. But you can use one of those to implement this. If you do, though, you're going to need to do what I'm calling queue per confidentiality level. Now, QPid does have access controls, but once the data is on the queue and you have access to that queue, you can read that queue. So QPid's access control isn't enough. You have to provide the assurance that if you connect to that queue and you can read it, that means you have access to every frame on that queue. So let me just give a quick example of what has to happen when you have queue per confidentiality level. So imagine you have 4 frames and it's produced by some agent. I just drew that as a video camera because I'm using the term frame, but it doesn't have to be. It could be anything. And you have the frames in order, frame 1, 2, 3, and 4. And you can assign a confidentiality level of A or B. And I'm just being really abstract here, but it could be whatever you want the confidentiality levels to be. And so you can imagine once you start sending these frames, if you sent this first frame, the producer is going to have to copy each of those frames to the queue that matches the frame's confidentiality level. So in this case, you're going to have to copy that frame 1 to queue A and to queue B. Now, in the case where you have frame 2 where it only has a confidentiality level of A, that just goes into the queue for a confidentiality level A. And then for the other frames, I mean, again, you're just going to just copy it over like so. And then you can see that on the bottom, you only just have the frames that have a confidentiality level of B. And at the top, it has the confidentiality level of A. Wow, big word to say after lunch. Too many syllables. Anyway. Now, this is fine as long as you have just a few levels. But imagine what we were talking about earlier today where folks were trying to, provide different levels per consumer. I mean, you can maybe have hundreds of these, right? And even if you get into the classification levels for, top secret documents, you actually can get into the hundreds. And so you can, if you, like in this case, if we even decided just to make it so you can have it, you wanted to only allow someone to see things that only labeled with A. That's a whole nother queue, and you're going to have to do more copying. So that's going to be a problem. So what we really want is just a single queue for all confidentiality levels. And in this case, that single queue will contain all the frames, right? And then consumers will only be able to read frames for which they have access. So this is essentially a Accumulo table, right? And in this case, and I'll just quickly go through this animation, is everything goes into the queue, and then the consumers only just read what they have access to, right? So in this case, that the consumers with access to A will only get that frame 2, and everything else. Consumers with access to B can get the other frames. All right, so that should be straightforward. Now, how do we implement this? So, again, you can't do this in QPid. At least I don't think so. So let's try this with Accumulo then. So then the way we're modeling this with Accumulo is that we're going to implement an unbounded buffer, right? So if you took computer science at the undergraduate level, you probably took a course in operating systems. I have a former student here, and I remember we always spent a lot of time on this. But you're going to basically have a unbounded buffer problem where you have a single writer multiple readers. And usually in that problem, you have to do a synchronization on the size of the buffer. But when it's unbounded, you don't have to do that synchronization. So if we use Accumulo, we can, in a sense, technically or theoretically have a very, very large bounded buffer. So large, I mean, you can have 10 to the 49 entries. So that's almost infinite, right? But, obviously it's not, but that's good enough. That basically means that we can keep writing to the end of the buffer and never have to circle back, most likely. I mean, I couldn't imagine anything writing that many entries. But there's a problem, obviously. You don't want to have a table that large. And I'll talk about how we deal with that later on. So how are we implementing this in Accumulo? We're going to have basically a row for each frame. The row ID is just going to be a string of 32 characters from the set A to Z. And they're basically, we have basically it's a number with the 26 digits. So that's how we get to 10 to the 49 frames, because it's 26 to the 32 different frames. So the first frame is going to be labeled with just all A's. Second frame is all A's with the last character B. And the 27th frame is going to be, all A's and B, then the last character is going to be A. And you just keep doing that over and over again. So the security label is going to be the confidentiality level that we want that frame to be at. So we organize the columns in a certain manner because we first tried to put the entire value in in just one column, but that's a problem if you have large values, right? So if you have a small machine, let's say if you wanted to do this on a 1 gigabyte machine, you're configuring Accumulo to use maybe 512 megabytes. Then if you get like very large values, even like say just 2 megabytes, the writes don't happen, I don't want to say instantaneously, but you can request a read before the value's actually been written out to disk. And so you'll do a read and you won't get all the value back. So what we had to do is then in the column indicate what the size of the value is, so when you did the read, you'll know how much data actually you needed to read for the value. So in particular, what we did is you took a frame, you can break it up into multiple columns. The first column is just going to tell you how big the entire frame is, and then the other columns are going to have a portion of that frame. And so the column qualifier for the first column is the total size of the frame, so you'll know exactly how much to get. And then when you read a second column, if you can't get all the columns at once, because we did it so that we didn't fix the frame size. I mean, you can have 10 megabyte frames. You can even have, again, we didn't limit it. You can send 1 gigabyte frames, but I don't think anyone would actually do that, but it is possible. So it's depending on your setup. You may not be able to get all the columns at once because it could be hundreds of columns. So we label the columns in the column family, and the column qualifier for the second, third, and so on frames is the size of the value for that column. So I hope that makes sense. If you have a question, just let me know. And also, if you do have a question, speak up really loud because I have ringing in my right ear. Hope it goes away soon, but I was a DJ in college and kind of messed me up. Anyway, so here's a simple example. If you have a 1 kilobyte frame, you can divide into 2 columns. That first column has the size in the column qualifier, which is 1024. The second column is going to have, in this case, we're 512 because we're breaking up the frame into 512 byte segments. And in the second column, cauliflower will have 512 as well. And this is configurable. You don't have to have 512. And I'll talk about how we adjusted the frame sizes when I talk about our results. So here's the design of a proof of concept that we created because we wanted to actually see how well this would work. I mean, how well Accumulo will work if we wanted to send frames at, and we're trying to aim like 25 frames per second. So at the top, we just have a single node instance of Accumulo. You have a producer, which is going to write the data, and the producer obviously is going to, whatever it does to actually generate the data, then it's going to use an unbounded buffer writer, which is basically a Accumulo client, and it uses that to actually write to the buffer. And a producer also is going to have some state, and that state is just actually use that state for fault tolerance. So let's say if the producer crashed and it was intended to write, let's say it intended to write 100 columns, but it only wrote 50. We don't want it to start at row A, all A's again. We wanted to start at the 50th one, so it can write out what was the last row that the ID of the last row that was written to the buffer. We also have a consumer, which contains an unbounded buffer reader, which is again is a wrapper around an Accumulo client for a reader. So it's a simple scanner, and the buffer writer is a simple batch writer. We didn't do anything, on the server side for this proof of concept. But again, it has some state where it knows what was the last row it read. We also have another component for deleting rows. So again, there's the potential we can have 10 to the 49 rows. We don't actually want to have that many. So periodically, we run a client that just goes and deletes rows that are older than n seconds. You can figure in whatever you want it to be. And also there needs to be an authorization service, and this is going to hand out to the producer and the consumer what the its access rights are. And these will be turned into the security labels that the producer and consumers use. There's some improvements we could have made that we realized after the fact. And also, some of it was intentional because we wanted to compare bare bones Accumulo to bare bones QPid. And one thing was, again, I think I didn't mention this, but I did say we did use the batch writer, but we actually aren't batching the writes. We flush on every write. So that definitely can be improved. And there's a lot of polling for the readers. So if the reader has read everything in the buffer, it's polling to see what's next. So that definitely needs some improvement, and we could, if we wanted to, we can probably just use a multicast where, the reader just sits and waits for a message, one byte message from the producer says there's something in the buffer, and then it can go get it, and we can eliminate the polling. So we wanted to compare what we did in Accumulo to a Q per confidentiality level implementation, and that was using QPid. So what we did was, or what we wanted to do is see what's the average time to read and write a frame at a specific rate. So imagine you're streaming data. You want to see if you could. We wanted to see if, for example, could we stream uncompressed video at 24 frames a second. So that's about 50 milliseconds. And uncompressed video somewhere about 2 megabytes a frame. And then we also took something that's a lot smaller as a because we figured that I really thought QPid would be faster, and I'll show you later. In some cases, it isn't. And we knew that Accumulo QPid should be faster for 2 megabytes, and QPid should definitely be faster for 8 kilobytes. But we really wanted to see how much faster, right? And in our test, we used a number of consumers, 1, 10, 100, and 1,000. And we tried at different confidentiality levels, 1 and 5. And again, no special configurations to QPid or Accumulo. So, let me say one other thing. So, for Accumulo, we use Amazon Cloud, and we use, which one is that? The M3 large. So I think that's about 8 gigabytes of RAM. We use the Cloudera distribution of Hadoop, and we use Accumulo. We just took the 3 gigabyte configuration, no changes to that for Accumulo. And QPid, we made no special configurations other than we made the queues can be 2 gigabytes. So on this slide, I'm showing you the transfer rates for one consumer, one producer, 50 millisecond frames. And on the blue side, and I wish I had a pointer because I really want to go over. From New York, I really want to use my hands. It's kind of hard not to. On the blue side is Accumulo, red side is QPid, and I got my pointer here. So if you look at these results, you notice obviously that the access levels do not impact the read and write times for Accumulo, but they do impact them for QPid, obviously, because there's multiple copies. What was interesting was you expect that it'll just be 5 times, the write time will increase 5 times more than for 1 access level than for 5 access levels, but that's not the case. And there's probably some, other factors involved with the writing. For example, again, when you have the multiple queues on QPid, all the queues are in memory, and it's possible that there was some context switches going on as we were doing some of the writes, and that could be why that increased. But anyway, this is expected, right? That if you're writing things 5 times, obviously it's going to be worse than if you're doing it once. But notice the significant difference. You got 4.3 milliseconds for Accumulo and 47 milliseconds for QPid. And I ran this a lot of times because I wanted to really make sure that I didn't get these numbers wrong. But the numbers don't lie in this case. And this also demonstrates that if you're at 8 kilobyte frames, you can get 50 millisecond frame rate, and actually even lower. But it doesn't work. You're not going to get that frame rate for 2 megabytes. For 100 consumers, we see that QPid outperforms Accumulo. So for QPid, the transfer rates are pretty much the same for one consumer. But for Accumulo, as you increase the number of consumers, the actual read times actually increased. And in the case for 2 megabytes, they increased substantially. So you're actually at 2 seconds per frame, which is not what we want. When you get to 1,000 consumers, it's even worse. For Accumulo, But it's better than QPid because you couldn't even test QPid with 1,000 consumers, at least in the configuration we did, because each of those, for each consumer, if you're using topics, you're copying, you have a separate queue. So you need 1,000 times 2 gigabytes of RAM, but I'm sure there's a way to maybe configure a QPid to make this work. But with just the base configuration, we couldn't even test it. But notice for QPid, the read times are, very high. You're talking about 18 seconds per frame. And that was affected, that again, the polling did impact the read times. So if you look at, I'm sorry, I said that wrong. The polling for the polling that the consumers did affected the write times of the producers. So if you look at what I circled in red, that's when we did writes at 50 milliseconds, but reads were at 30 seconds. So in other words, the 30 seconds is just the amount of time that the consumer blocks before it goes and checks to see if there's any data in the buffer. So it's only going to it's only going to block if there's nothing in the buffer. So that's why you see, it's not going to always be 30 seconds or above 30 seconds the read time. So why do we think that's happening? So several things. It could be disk contention for the actual having to read from the disk so as the writer is writing out the 2 megabits and you have thousands of consumers asking for those frames, you have to do 1,000 copies of 2 megabytes, which we think could be a problem. And it also could be, and I'm not sure about, maybe something in Accumulo. I don't know if it's requires exclusive access to the index as it does the write. If you're trying to do a read, if you're making a request to see what's the last. All right, I'm almost done. You got 3 minutes. All right. Wow, and that said I was going to be short, right? All right, sorry. So let me just whip past this. This is like 2 more slides to go. So we did see that in some cases that sharing the NICs or the network cards was a problem when we got to 100 consumers and 1,000 because when we were doing this on Amazon cloud, so we couldn't spin up 100 different VMs, so we had some of the consumers had to share. You can see as they shared from 100 to 1,000, even for 8 kilobyte frames, the times increase. All right, so in conclusion, I want to conclude that we think Accumulo will be suitable as a backbone for message queuing system. It does outperform QPid, especially if you're going to have complex attribute policies that you need to implement. But it doesn't perform that well for large frames. It's reasonable if you have a small number of consumers and you have no more than 5 frames per second, I think that fits many use cases. And if you have small frames, you can get to 100 consumers and get to 40 frames per second. Take any questions? That's a good question. No, I didn't do that. And I'm not sure how that would help. Does it make much of a difference on a single node instance? So we restrict it to only just one producer.
Yeah, so 1 and 1 would work. The minute you have more than
More and more, you got to use a separate table. Yeah, you have to use separate table. That's why that.
may not scale those 20 with enough.
Yeah, you're right. It may not scale. That's when you could introduce, a clustered version to help with that. But that's something that we can try. I probably that's probably my next step.
Also, if you increase the number of
Right, yes. So the reason why we did it this way, because we wanted to try the case, well, what if you wanted to do this in an environment where you have basically a laptop as your device, and you need to provide this kind of confidentiality level. That's what the reason a single node instance initially tried it with, just 1 gigabyte of RAM. No, but I'm not sure if Storm is going to provide the confidentiality level protection. Yep. Yeah. All right, that's it? All right, thank you, everyone.